Hi everyone, welcome back to the course on Microsensors and Nanosensors, and we are in the 7th week where we are going to discuss about force sensors. This is the first lecture on this force sensors. Let us understand first about the force, and we will slowly see that what kind of force sensors we are going to discuss in this course. So, the idea of this force is inherited in the Newton's first law, which suggests that a body remains at rest or in a motion at a constant speed in a straight line unless it is disturbed by a external force, right. Similarly, the Newton's second law suggests that at any instant of time, the net force on a body is equal to the body's acceleration, which is multiplied by the mass, or the rate at which the body's momentum is changing with the time, right. So, when force is applied to a free body, of course, this body is not anchored to any particular fixed position or to another body. It gives the body an acceleration which is in the direction of force. Okay. Therefore, the force is considered as a vector quantity, and mathematically this force can be given as mass into acceleration, right. And we can also discuss this in terms of momentum, and the force can be given as m1 v1 minus m2 v2 divided by t1 minus t2, or rate in change in time. Or if the mass is fixed, I can say that m v1 minus m v2 by t1 minus t2, or m v1 minus v2 by t1 minus t2, right. This is how I can define this in terms of momentum. Okay. If you see this equation carefully, F equal to m into A, in this equation the SI unit for mass is say kg, and acceleration can be written in terms of position as del square x by del t square, right, double differentiation of position vector, right. So, it is the distance and time. So, in acceleration, the SI unit for distance and time is in meter and second. So, 1 unit of force is the force which will accelerate 1 kg of mass to an acceleration of about 1 meter per second square, right. And this 1 unit of force that I am discussing is known as 1 Newton, okay, or 1 Newton of force. Now, considering this definition, if I define this force for a say car, okay, of say 100 kg, to have an acceleration of 1 meter per second square, you will need around 1000 Newton force, or about 1 kilonewton. Okay. In this course, we are not going to discuss about these forces. Since this is a course on microsensors and nanosensors, we will be mostly dealing with force of the order of 1 micronewton or 1 nanonewton, or even sometime 1 piconewton also, okay, or few micronewton, few nanonewton, or few piconewton, right. So, for a vehicle of weight around 1000 kg, you have a force of around 1000 Newton, right. So, you can understand that for a movement of a nanoparticle, okay, or microparticle, with certain acceleration, you will need this order of force, right. So, in this course, we are going to discuss about the sensors which can detect the force in this order. Okay. Now, let us understand this concept of force in terms of the body, okay, what kind of body it is and how this force is defined. In the module 8, we are going to discuss about pressure sensors, and all these sensors are interlinked with each other. Okay. So, whenever a pressure is measured, it is mandatory to measure the force. You know the mathematical relationship between force and pressure, right. So, force is typically measured in the context of solids, while pressure is measured when dealing with mostly liquids or fluids. These fluids can be not only liquids, but it can also be gases, right. So, in other words, force is considered when it acts on a specific point. Okay. So, when you talk about applying some external stimuli, okay, or some constant on a solid body, okay, it is mostly defined by force. However, say if you have confined a liquid inside a balloon, for example, okay, or inside a vessel, the pressure that this liquid is applying is actually is mostly categorized under pressure, and usually we avoid talking about force in such a scenario. That is why I have just mentioned that force we recall when we discuss about solid surfaces, while while dealing with liquids or gases, we mostly talk about pressure. Okay. So, pressure is measured when force is spread over a large area. That is what is happening in a balloon where liquid is trapped, or say for example gas is trapped. Okay. So, this gas is pushing at each and every point of this balloon. So, I can say that force is spread over the larger surface area of this balloon. Okay. So, what is the exact use of this force sensor? We will see it in a while, but in a nutshell, force sensors is very useful in case of micro manipulation and micro assembly. Okay. Not only micro manipulation, but at nano manipulation as well as nano assembly kind of things. Okay. There are a lot of differences between a macro world and a micro world. Okay. So, when I say about macro world, whatever tangential is we see around us, okay, is a macro world. For example, this pen that I am using to write on this notepad is a part of this macro world. Okay. However, the nanoparticle, or if I am using for example a surface to write, okay, and if it is say for example the ink is based on some polymer, okay, or polymeric ink or something else. Okay. So, the nanoparticle of this ink is a part of micro world, okay, or nano world. Okay. So, these two worlds are totally different, and how you deal in terms of force or pressure at these two world is totally different, and that is why we need special skill to learn for this micro and nano force sensors. Okay. So, in contrast with the macro world, the micro objects in manipulation are easy to be destroyed if the contact force is not reliably detected and controlled. Okay. Now, let me give you an example, to understand this. Okay. Consider that I have a pen. Okay. I have a pen. I want to move this pen from point X to point Y, okay, by a robotic hand, for example. Okay. I am not touching this pen, I am using a robotic hand to grip this and to move this from point X to point Y. All right. So, to move this pen from this point X to point Y, what I will need is, I need two different kind of forces to understand to move this. Okay. The first is, I have to understand the gripping force. Okay. Like if I want to grip this pen, okay, with my hand, or say with a robotic hand, I should know that what amount of force I will exert on this pressure on this pen, so that this pen is not destroyed. Okay. If I press it very hard, it can be crushed, or if I apply large force on this pen will be destroyed. Okay. So, the first force that I will need for this movement is the gripping force. Okay. Second force I will need is what amount of effort it will take to bring this pen from this point to this point. Okay. So, these two different forces you will require. Okay. So, this is in the macro world. All right. Now, consider that you are building a sensor using say gold nanowire or silver nanowire. Okay. I have a interdigitated electrode which I am giving example since lecture 1. Okay. Say this is my electrode. All right. Say this dimension of this electrodes are say this is say 100 nanometer. The gap between these two electrodes, two fingers, is also say 125 nanometer, right, and this total distance is around say 900 nanometer. Okay. These pads are of around say 700 nanometer. Say I have this kind of structure. Okay. Now, using a nano manipulator, okay, what I want is I have say 20, I have around 20 gold nanowires for example. Okay. The dimension of gold nanowire is around say 10 nanometer in dia and say 130 nanometer in length. Average length is around 130 nanometer and average diameter is about 10 nanometer. Okay. Now, I want to put this gold nanowire on these electrodes to make a sensor out of it. Okay. Again, I will need two different forces to understand to bring this here. Okay. One is the nano manipulator's gripping force, okay, how it should grip, and second force will be how it will be brought here, right. Now, in this macro world, so this is micro world I am talking about or nano world. Okay. Now, in this macro world, when I wanted to grip it and I wanted to lift it and put it to point y, okay, say I have exerted say F1 or Fm I am calling Fm amount of force to grip it, okay, and say Fw amount of force to move it from this point to this point. Now, you have you can have more deviation in Fm as well as Fw. So, Fm can be plus minus say 40%, okay, or say plus 40% also. So, if say Fm amount of force is needed to grip it, if you exert Fm plus 40% of Fm, then also this pen will be not destroyed. Now, consider in the nano world, okay, if you wanted to lift this gold wire and you wanted to put it here, okay, and it requires say Fn amount of force, and in that case if you exerted say 10% of Fn, okay, so the required force was Fn, but you miscalculated and now you are applying Fn plus 10% of Fn, there is a high chance that this gold nanowire will be broken. Okay. Forget about lifting it and putting it over here. All right. Therefore, I have mentioned that In contrast with the macro world, the micro objects in manipulation are easy to be destroyed if the contact force is not reliably detected and controlled. Okay. I will give you some example of this force sensor where this kind of changes matters a lot, particularly in case of some surgery or in case of some operations, say for eye operation and some other operation, where these force sensors or these micro manipulators play very crucial role. Okay. Say in the process of micro assembly, force feedback in every step is required to ensure the success of assembly. Okay. If feedback is not there, the assembly will not happen. Okay. In micro robotics, achieving efficient and secure grasping task at micro scale needs the use of micro manipulation system, as we have discussed now, okay, with force sensing which should be suitable for handling micro scale objects and nano scale objects. Okay. Another important application of micro force sensing is in the eye surgery, okay, in which the doctors apply image guided intervention using optical coherence tomography. Okay. So, if the force sensing is not correct, it may manipulate something else in the eye, okay, which is not required. Okay. A sense of touch in such application is needed to improve the outcome and increase the safety. Okay. There can be a number of force sensors at both macro level and micro level. Okay. It can be based on simple strain gauge, which also leads to load cells. Okay. You have force sensing resistors, you have piezoelectric sensors and so on. Okay. And application of these micro force sensors are in medical, as I have just mentioned, in robotic surgery, okay, prosthetics, then wearable devices, electronic skin. Okay. In all these cases, I mean, this is a small list, the application is much beyond this. Okay. At industry level, you require it for micro assembly, say for quality control and other applications. Robotics, it include electronic skin also, as well as for precision gripping and all, you require these force sensors. Okay. In fact, tactile sensors also require some force sensors. Okay. Then of course, in biological research, you require it for cell manipulation, microfluidics and other purposes. Okay. So, this micro force sensors are basically divided into two different classes. One is the quantitative force sensors. These quantitative force sensors detect the applied force and convert it into a corresponding electrical signal, say for example, strain gauge or a load cells. Okay. Then you have qualitative force sensor. It shows whether the applied force exceeds a certain threshold or not. Okay. As I have mentioned that for several applications, these kind of qualitative force sensors are required, where you actually do not bother when force is below a certain threshold, but you become very careful if the force applied is beyond the threshold. Okay. For those kind of application, force sensing resistors or FSR are very crucial. Okay. Now, the methods of sensing forces can be based on several phenomena. Okay. The most applicable choice for these force sensors are by simply balancing the unknown force against a gravitational force of a standard mass. Okay. So, if you balance out the gravitational force of a standard mass, you will know the exact force. Okay. So, similarly, by measuring the acceleration of unknown mass to which the force is applied, you can indirectly find the force. Okay. Then by balancing the force against an electromagnetically developed force is another way to find this force or to find the applied force, or is the principle behind many of the force sensors. Okay. There is another way by which you can measure the force is by converting the force to a fluid pressure and then measure that pressure. If you know the area, you can calculate the applied pressure. Okay. Then another way is by measuring the strain product in an elastic member due to unknown force. So, in an elastic membrane, if you know the strain, you can calculate the force, and that is how a strain gauge or strain gauge based force sensors work. Okay. So, based on the working principle, force sensors can be divided into several types, or it can be classified under various heads. Okay. The first type of force sensors that we are going to discuss in this module is on strain gauge based force sensors. Okay. However, there are, it has certain limitations. So, we will also study other kind of force sensors like piezoresistive force sensors. Then piezoelectric force sensors is also there. We will try to cover that also. And then we have capacitive force sensors. Okay. On the magnetic phenomena, we have piezomagnetic force sensors. Okay. Then we have optical force sensors. We also have vision based force sensors based on image processing techniques. Okay. And then we have electroactive force sensors. We will try to cover all of them in at least in very brief. Okay. So, let us discuss first about the strain gauge force sensors, and then we will take each of the sensors that I have just described in brief. Okay. So, strain gauge based force sensors is among the widely used method to measure micro scale forces, particularly when you are not worried much about non-contact based force measurement. So, these strain gauge based force sensors are basically more useful while detecting the contact forces. Okay. So, strain gauges are mostly attached to the substrate using a specific adhesives depending on their required lifetime. If you require higher lifetime, the adhesive will change, but then it will affect the overall cost, and also you have to see that if that adhesive is suitable for the substrate on which you are attaching it. Okay. So, a typical strain gauge based force sensors looks very similar to this, where you have attached this external strain gauge on top of this particular material on which you are trying to measure the applied force. Okay. So, as you know, there will be some deformation if I am talking about strain. So, if the strain is say del A, okay, I can calculate it by this particular formula. Okay. So, sigma, you know, that is force by or the stress is force by area. If I talk about Young's modulus in terms of Young's modulus, I can say that this is equal to Young's modulus into the strain, okay, or Young's modulus into del L by L, which defines the strain. Okay. So, by using these two equations, F by A equal to E into del L by L, I can calculate the applied force if I know the area in which I have applied it, okay, and the change in the length. Okay. So, by simply using this equation, we can calculate this, but then if you see the circuitry of this kind of sensor, it is mostly based on bridge kind of configuration, because it gives you better sensitivity. Okay. So, the use of adhesive in the strain gauge force sensors can lead to problems, for example, drift and sometime even the signal loss if the adhesion is gone. Okay. This is caused by signal transmission through the structured layer. Okay. Strain gauges are sensitive to the variation of humidity and temperature in the surrounding. So, the delta L that you have seen is not only because of the strain applied or the force applied, it can be due to the changing ambient parameter, particularly the humidity and temperature. Okay. So, Wheatstone bridge, as I have just mentioned, Wheatstone bridge configuration are often used to overcome such problem in the strain gauges. Okay. Then also there are various disadvantages of these strain gauges which cannot be countered easily, like strain gauges cannot be recovered after being overloaded. Okay. So, if say this is the materials strain versus stress analysis curve. Okay. Say if the force applied is making the deformation in such a way that the material is still in elastic zone, it is perfectly fine. Okay. Once it crosses the elastic limit and then it crosses the yield point, okay, the calculations that it gives or the measurement it gives is mostly wrong. And you can understand that once it crosses the ultimate strength point or the breaking point, things is beyond your control, and even the strain gauge will not be reusable in future. Okay. So, the problem with this strain gauges is once you overload it, it cannot be recovered back. Okay. Once it reaches its plastic region, it cannot be brought back again to the elastic region. Okay. Then due to their mechanical characteristic, they have exhibit high hysteresis and often exhibit a nonlinear response. Hysteresis we have discussed in the first module, and we are talking about that particular hysteresis. Okay. So, if I summarize the disadvantages of strain gauges, it can be beyond these two points. It can be like, say, temperature sensitivity of the strain gauge, as I have just mentioned, that due to variation in the ambient condition, particularly at the temperature front, the strain gauge results vary at large scale. Okay. The signal output usually of this strain gauge is low. Okay, and you may require some special kind of amplifier to amplify the signal. Okay. The devices are fragile mostly, so you have to handle it with care. Okay. The dynamic response of this strain gauge are mostly limited. Okay. And the creep and drift of this device is very important to be considered while you are using it for measuring micro forces or say nano-Newton kind of forces. Okay. There can be various remedies. Okay. These limitations are mostly overcome by using thin film based strain gauges. Okay. So, avoiding this wire kind of or this adhesive kind of structure. So, directly if you can have thin film based strain gauges, of course, this thin film can be deposited by various physical vapor deposition technique or various chemical vapor deposition techniques. Okay. So, a thin film strain gauge consists of a thin piezoresistive material which is deposited directly on an insulating surface of a strainable device. Okay. So, the thing is very simple. You simply coat the piezoresistive material on the insulating surface of the strainable device. Okay. And you measure the strain in the piezoresistive force sensors directly. However, this technique also suffers several disadvantages, particularly although you have brought the material in the form of thin film, but still the temperature sensitivity of this thin film based device is still very high. Okay. The signal output is still not much improved. You have at least improved at the fragile front. So, the device is not that fragile. Okay. But then it deals with complex mounting. Okay. So, you cannot deposit anything on everything. Okay. So, if you have a piezoresistive material, say if your material is X and there are several say insulating surface of the device where you actually want to measure the strain, okay, or the force. Okay. Say you have A, B, C, D, 4 different surfaces. So, X can only be deposited at the surface C, and it cannot be deposited at A and B as well as D. It will simply peel off at the surface of A, it will not stick to the surface of B, or it can say it will simply peel off from the surface D as well. Okay. So, the mounting of this thin film based strain gauge based force sensors is not easy. The mounting is actually complex. Okay. The dynamic response of this kind of thin film based force sensors is limited, and it also suffers from hysteresis. Okay. Then it suffers from fabrication complexity. Okay. So, for example, if you want to measure say micro force on the surface of a say sensor, okay, say bendable sensor, okay, you are trying to find that if I apply a force till what angle it can be bended. Okay. Now, you want to apply a thin film based strain gauge. What you have to do is you have to take this inside a say PVD system. Okay. Now, PVD system will have limitation that it may not allow this kind of device, or it can not allow this kind of substrate to insert into its chamber, okay, or at its substrate holder. Okay. This device can be of various shapes which may not fit over here. Okay. So, there are fabrication complexity associated with this thin film based strain gauge force sensor. Okay. Then I have already discussed about substrate compatibility in the previous slide. Okay. The mechanical robustness of this kind of sensors are also low. Okay. The noise level of this kind of thin film based sensors are obviously little bit higher as compared to the wire based or the other kind of strain gauge based sensors. Okay. Then this kind of film based sensors are difficult to repair, okay, and sometimes it is also difficult to repair, okay, because if say the piezo resistive material say X is very much compatible to surface Y, okay, Y is your sensor on which this bendable kind of device where you want to measure the force. Okay. Now, the addition of X on Y is so good that if you take out the say if by some mean if X is disturbed or is little bit destroyed, okay, now the way is you have to remove this X, okay, completely, and then again put another layer of say X in the form of say X1 at the surface of Y. Okay. But in the process there can be, it can happen that when you are removing this X, it may destroy the Y also, or at least the top layer of Y. Okay. So, repairing this kind of device or replacement of this kind of device is nearly impossible. Okay. Then the strain transfer efficiency is also not that great. The long term stability of this kind of thin film based strain gauge force sensors is another point where questions has been raised in the past. Okay. So, this is all about strain gauge based force sensors. These are the most basic kind of force sensors, particularly if you are using it at the micro and nano scale, okay, devices. Okay. We will discuss other advanced kind of force sensors in our next lecture. Thank you.